Hello everyone. So today we'll be solving Codechef Starters 123 Div-2. Let's get into it. First problem, maximize adjacent sum. Okay, so in this problem, you can go through a problem yourself. I'll just explain from the above what the problem is. We are given an array of size n, okay, and then there's a function which takes the current element and the next element and it iterates through the whole array from the first element till the n minus 1th element, and it iterates and it takes the maximum of the current element and the next element to it, and it sums these two values and we have to find the maximum value of the whole function. Okay, so let's take one example. So this let's take this as an example. Okay, so in this particular example you can see that mm, let's say this is a1, this is a2, this is a3, a4 and a5. If we take the maximum of these two, okay, sorry, the sum of these two, it will be a1 plus a2, this will be a2 plus a3, this will be a3 plus a4, this will be 4 and this will be 5. Okay, and this would be a4 plus a5, right? So if you do this till this, then you can see clearly that every element from this second element till the n minus 1th element gets added up twice, right? So this is the sum, right? It gets added up twice. So this would be basically uh, and we have to maximize this, right? So if we do, we have to maximize or minimize? Maximize. Okay, so if we keep the minimum value in the endpoints, that would maximize the overall value, right? Because we want to calculate all the bigger values two times and the smaller values, the smallest values one time, right? So basically we have to find the two smallest values and then add it only once, and then every other value which is uh, you know third smallest till the largest, we'll be adding it twice. So let's go to the code. This is our this is our input to the vector, then we sort the vector, and then if it is after sorting in the ascending order, if the value is either the 0th index or the first index, we add it once, else we add it twice. So that's it. So the main observation, the key observation was that every element from second till n minus 1th element would be added up twice, and the first and last element would only be added up once. So we need to strategically place the minimum value at the starting and the ending of the array. So that's it. Second problem. So we are given a permutation of length n. A permutation of length n is basically uh, an array starting from 1 going till n, 1 2 3 4 5 6. Let's say if n is 6, and the permutation is basically any permutation of these elements. So our function f is, we take the, by the way, this is a circular permutation, so 6, the element after 6 would be 1, right? That is what uh, this means, where a n plus 1 is equal to a1, right? So we have to take the minimum of the current element and the next element, and we have to sum the whole thing. Okay, so we take the minimum of these two, and then 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 these two. Okay, whatever the minimum is, we just sum them up. Now let's start small. Let's not go with n equal to 6. Let's take the example n equal to 3 and n equal to 4. And by the way, the n is at minimum 3. So let's say n is equal to 3. So we have 1 2 3. Now if we take the minimum of these two, it is 1, these two it is 2, and these two it is 1. So it comes to 1 1 2. Now is this the most optimal? You don't know. So let's take another permutation. But one thing, let's try to observe one thing. So what I observed early on is that we would like to, we are trying to minimize the whole sum, right? So we would like to place, we would not like the bigger values to be chosen, right? So we would like to maximize the utility of the smaller values like 1, 2, right? We would never like 3 to be chosen ever. Or if the n is equal to 6, we would not ever like to be to we would not ever like 5 or 6 or 4 to be chosen ever, right? We would like these smaller values to be chosen. So let's place uh, so it will always be optimal to place the smaller values starting from 1 and then place some really big values besides this, and then place, let's say, 3 and then place the bigger values, sorry, let's place 2 and then just place 3 and let's say 4 the bigger values beside this, so that 1 is chosen in these circumstances and 2 is chosen in these circumstances, and then in this, maybe 3 is chosen and this in this 4 is chosen, something like that. Okay, so we want to maximize the utility of the smaller values. So in this one you can see it, the best sequence that we can get the most minimum is 112, and you can do some other permutations as well. You'll find 112 only, so this value would be 4. For n is equal to 3, sorry, n is equal to 4, you can see one of the permutation, the optimal permutation given is 2413, 2413. So this would be 2, this would be 1, and this would be 1, and this would be 2, right? But now how did this person come up with this permutation, right? We have to come up with this permutation. So again, he took 1 and then he placed the two big values besides this, so 4 and 3. Okay, and then he just placed 2 uh, next to it, right? So this is 1, this is 1, this is 2, and then this is also 2. So it will be 1 1 2 2. This is 6. If we take let's take one more and it's equal to 5. Okay, so in this one it would be, we'll place 1 and then we'll place the two big values, let's say 5 and 4 over here, and then we can just place 3 over here and then 2 over here, something like that. Okay, so this would be 1, this would be 1, this would be 3, 2, and then 2. So one thing you can see is that we want to utilize our ones. How many times can 1 come in any combination? At least, sorry, at most 2 times, right? It can be the minimum with this side, and it can be the minimum with this side. So, and because 1 is the minimum, we always want to we always want the final output of this comparison to be 1, right? So we want 1 to be at least 2, we want 2 also to be at least 2, we want all the smaller values to be at least 2, so that we can never uh, include the bigger values, right? So that our final sum can be to the minimum. So in this particular case, it will be 1, 1, 2, 2, and 3. That would be 4 plus 2, 6 plus 3, 9. Okay. So if you do it like this, you'll realize that you'll see a pattern. Okay. The pattern is 1, 1, 2, 2, 3, 3. Then for n is equal to 7, it would be 1, 1, 2, 2, 3, 3, 4. So this would be 6, 10, 12, and this would be um, you know 12 plus 4, 16, something like that. So what we can observe is, if you see, the last value till which we are going is n divided by 2. So for if n is 4, the last value that we are going to is n divided by 4, which is 2. For 5, it is n plus 1 by 2, right? For even, it is n by 2, 3. For 7, it is 7 plus 1 by 2, 4, right? So just go to the code and understand this better. So if n is even, okay, find the length, which is n divided by 2. For, let's say, 6, n divided by 2 is 3, and then you can see it is 1 plus 2 plus 3 plus 1 plus 2 plus 3, 2 times, right? So this is n into n plus 1 divided by 2, and this is 2 times, so we can just remove the 2, right? So that is what we do, length into length plus 1, and we output the value. Okay, for the, if it is odd, if it is this, then we find the length. Okay, and this is basically 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4 minus 4, which is n plus 1 divided by 2, right? So that is what we do. We find the length n plus 1 by 2. If it is odd, n plus 1 by 2. And then we say length into length plus 1. So this is basically this. And then we subtract the length. And then we subtract the length n plus 1 by 2. So that is our output. Okay, let's go to the third problem. Minimum maximum 2. We are again given a permutation and we define the permutation as maximum, and we have to overall minimize the value. Okay, so in this particular case, again it is similar. We are given a permutation, so let's take this permutation 3. So let's say n is equal to 3, and then we are given a permutation, so let's say 1 3 2, let's say, and then we take the maximum rather than the minimum, so that would be 3 3 and then 2. um, okay, and then in this particular one, if we see carefully, mm, yeah, the total sum is, in this particular one I just saw a pattern, and again, I just did a mathematical calculation and that was able to solve the problem. So this is 8 if n is equal to 4. So this is one thing that you can actually do in your problem solving. Just sometimes you can't prove an assumption, and you can't have find assumptions, and then you can't prove a particular theory which unlocks the whole problem. So you can just see if you can see a pattern and then just go with the pattern. So in this particular one, as one observation that you can see is that we would like to maximize the utility of the maximum values. So unlike this one, in where we were maximizing the utility of the minimum values because we had to minimize, we would like to have as many threes as possible in this one, like, and then as many twos as possible, and then as little as one, because we want to maximize the bigger values, right? But obviously 3 can't come more than twice because it can be compared only to left and right side, right? Okay, so for n equals to 4, 2 4 3 1 is given. Okay, 2 4 3 1. So this is 4, this is 4, this is 3, and then this is 2. Okay, so this is basically 13, and then for n is, so it will be 5. So if we see over here, this would be 5 5 4 2, and this would be 3. So this would be 5 5 4 3 2. So that is 19. So if we see a pattern, you can see a pattern, and if you do it for 6 and is equal to 6, what you'll find is 5, sorry, 6 6 5 4 3 2, because obviously 6 is greatest, so 6 will be at least utilized 2 times, and you try to um, utilize every single other element. It'll, the besides the most minimum element, every single element would be utilized at least once, right? So this would be 12 17 21 26. So if you see, the difference over here is 5, the difference over here is 6, the difference over here is 7, and so on, right? So this was basically the pattern, and let's just go to the code. So if n is equal to 3, I straight away output 8, and else you can see that if n is equal to 5, let's say, right, then what do we do? What we do is, this is basically, um, just a second. This is basically 8 plus 0. This is 8 plus 5. This is 8 plus 11. This is 8 plus 18. So what we are doing is, um, l- we so what we can do over here is that, we keep the initial value 8 over here, and then if let's say n is equal to 6, what we do is this value is always n plus 1, right? If n is equal to 5, this is n plus 1, right? So what we do is we find the sum from 1 till n plus 1, and then we subtract 1 till, so what is the minimum value? If n is equal to 6, the minimum value is 2, right? So if n is equal to 6, what is the minimum value? The minimum value for any particular n, the minimum value is always 4, because we are adding up from 5, 5 plus 6 plus 7, right? So 1 plus 2 plus 3 plus 4, this value we don't want, right? So uh, we just sum from 1 till n plus 1, and then we just subtract uh, 4, 3, 7, 8, 9, 10. We just subtract them, and then we just add 8, which is the value for n is equal to 3. Yeah. So we start with 5 and with n plus 1. So what we do is, this is sum first, which is 10, the sum of the first four elements. This is sum second, which is the sum of, uh, you know, n plus 1 into n plus 2 divided by 2, because end is n plus 1. So we just do n plus 1 into n plus 2 divided by 2. And then, so this finds this whole value, and then we subtract minus 10, and then we just add 8, which is the our base value, because over 8 we are adding 5, and then we are adding 6, and then we are adding 7. Okay, so we just subtract these two, and then we just add, and that's it. Okay, let's go to the fourth problem. Check adjacent sum. Okay, so in this again we are given n numbers, and we have to take the sum of the current and the next element. And then we are given q queries, and each query has an integer x. Determine if there exists a rearrangement of array such that the function value is equal to x. So the sum of pairs, is it x or not? Does an arrangement like that exist? Else print minus 1. Okay. And if you see, the number of test cases are low, 50, and n is 50, and x is only 10 power of 6. So most likely, if situation is like that, it will go to uh, order of n square and cube. We can go and try to implement that kind of an algorithm as well. Okay, so just a second. Yeah, so one thing to observe here, that I observed, is that, let's just take one example. Let's take this particular example: 3 5 and 1 1 2. Okay, so 3 5 1 1 2, and one of the queries, let's take 5. Okay, or let's take 6 6. Okay, so x is equal to 6, n is equal to this, q is equal to this, and these are our elements a1, a2, and a3. Now can we have a permutation of this, so that a1 plus a2 plus a2 plus a3 is equal to 6, right? So again, if you see, if we all the elements besides the first and the last element would get added twice, right? So what I thought of doing was, I'll just take the sum of all the elements twice, and then I'll have to just reduce two elements from the whole sum, right? And I'll have to just find the indexes of those two elements, which I have to reduce from the total sum, because the total sum multiplied by 2 would be constant. So that is a constant. We can access it in order of 1. And then I just find these two. I just iterate over these two values, I and j, and see if I subtract these two values from the total sum, am I getting my x or not, right? So that is the whole problem. So for this particular one, what we can do is 2 plus 1 plus 1, that is 4, into 2, which is 8. So the total sum multiplied by 2 is 8. So this 8 is basically a1 plus a2 plus a2 plus a3 plus a3 and plus a1, right? And now we have to find these two values to subtract from this so that it becomes this, right? So let's go to the code. So what I do is I take the input and I take the sum. I take the sum and I multiply whatever the value is by 2 times and then add to the sum. Okay. And then I take a multi-set. Okay. Uh, just a second. I just yes. Yeah. Over here I go on a loop on I and j. So basically we are choosing our two elements, and I can do this because the value of n can go up till 50 only. So the number of test cases are 50 into 50, and then this can go up till 50, and this can also go up till 50. So overall it will be only 50 into 50 into 50, that is 10 power 5 operations only. And then we are given q queries, which is 50 as well. So, and just one rule of thumb in general in all the online judges, the number of operations that are allowed is approximately 10 to the power of 7 till 10 to the power of 8. So this is way less than that, so we can do a n cube solution. This is basically n square solution because the number of test cases are 50, that's why I said n cube anyways. So if I is not equal to j, so if we have two different elements, just add them up and then subtract it from the sum. And then because we need to, in the output, they are demanding the values, they are demanding an arrangement of the values, right? So we'll need to know the indexes of these two elements, which we will be placing at the start and at the end, right? So that's why whatever value we get, we are mapping that value to a pair. This is basically make pair. MP is make pair. We are making a pair of these two indexes, right? Then we sort this. No, sorry, this is not required. This is, I won't be using this. This is just random stuff. So let's now go to every query. So we take the input x, and then we see, can we find x in our map? If we can't find x in our map, we just output -1, because there are no two elements. If we subtract them from the total sum multiplied by 2, we will ever get our value x. So the output is -1. But if we do find in our map that value x, we take a deck and we add every element which is not either the I value that we had over here or the j value that we had over here. The two values that we basically picked. Okay, if it is not any of these, we add that particular value from the vector to our answer. And then we push the two values that we don't want in our uh, that we only want once in our uh, series. So we push one value in the front and we push one value at the back of the deck, right? So the two uh, values would be at the start and the end of the map, and then we see out the whole answer. So that is it for problem C. Oh, sorry, problem D, I think, right? I think we are on the fourth problem. Yeah, problem D. Let's go to problem E. Yeah, so this is a really interesting one, and I thought that it would be really complicated, but turns out it was not that complicated. If we just see the accuracy, it is really low, 21%, and really low acceptance rate. So let's see. Alice and Bob, the two classical culprits, are playing a game with n stones. Alice, in her turn, has to take at least one stone. So there are a lot of stones, a pile of stones, tuck, 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 tuck. and then Alice comes and takes at least one stone or more than one stone. Okay, so Alice can take up to A stones, while Bob can remove at least one stone or up to B stones. The person who takes the last stone wins. So basically, the person who isn't able to take any stone loses. So the what they are trying to achieve, both of the players, is they want to take so many stones so that the other person won't have any stone left to take. Predict the winner of the game if Alice goes first. The coders are always biased towards Alice, anyways. In Yeah, so let's take an example. Let's say n is equal to 12. So let's say there are 12 stones. So I'll just say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just make it 10. Okay. Now, let's say, so, I want to give you a sense of how I was going about this problem and how I was able to arrive at the conclusions and assumptions that I arrived at, and then build the solution. So initially what I did was I just assumed, let's say n is equal to 1. Okay, and let's say Alice's number is 3 and Bob number is 2, just for example. Okay, so Alice can take up to 3 and Bob can take up to 2. So I just thought that for Alice, if there is n equal to 1, Alice wins. If it is n is equal to 2, Alice wins. N is equal to 3, Alice wins. For n is equal to 4, who wins? And Alice is going first, right? So what Alice will do is Alice will just take 1, so this will be gone, and then Bob will be forced to take either this or this, but he can't reach this. So because he can't reach this, anyways, Alice will just come from over here or from over here and just remove everything and would win. So Alice wins this one as well. And then if Alice is over here, then he can just remove. So this is what I was doing while building solution. So Alice can just remove these two, and then Bob will have to again remove either this or these two, and then Alice can just remove either this or these two, and Alice wins again. So I realized that Alice would always win. And if we want to prove this theory, that if Alice says Alice can pick more number of piles from more number of stones from the pile than Bob, Alice would always win. And why is that? So let's say, over here we have Alice has 3 and Bob has 2. So just see this. Bob can pick two stones, right? He can pick these two, right? Now the thing is, Alice can remove Alice minus Bob number of stones. So over here it would be 1, right? So Alice, just a second. So Alice could be sitting, let's say over here, Alice is sitting, and Alice could remove these many number of stones. So one stone, and Alice would again be in the same position, and let's say Bob removes this particular stone. Okay. So what? And now Alice is over here, right? So if Alice wants, Alice could have directly come to this position as well. How? By removing two elements. I don't think my explanation was very clear. Wait, let me think how to explain this in a better way. See, these are Alice's turns. Okay, so 1, 2, 3, 4, 5, 6. So let's say Alice can remove 6 stones from the pile, and Bob is less than Alice. Okay, so Bob can remove less stones than Alice. So what Alice can do is Alice can force Bob to always Alice can be at any position basically. Why? Because Bob is less than Alice. Alice can just remove one, and because Bob is less than Alice, Bob can occupy only these areas, right? Only these areas Bob can occupy. There's at max. And then again over here it will be Alice's turn. So over here it was also Alice's turn. Over here it was also Alice's turn. So Alice can force on the game where Alice wants to be, right? Because Bob is less than Alice. Bob can never outposition Alice from any position. Why? Because Alice can subdue completely Bob inside it because Bob is less than Alice. So it can. So let's say Alice is six and Bob is, let's say, five. Alice can just remove one, and then Bob will completely be inside of Alice, and then Alice can again be over here. Okay, if Alice wants to be over here, let's say Alice wants to be. Let's say this is four. Then Alice can just remove uh, again one, sorry, two, and then again Bob will be inside of this, right, somewhere inside. So let's say Bob removes two. Bob, again Alice is over here, and it can just remove this, and again it can be, right. So that is the reason why if Alice is greater than Bob, so the conditions are Alice greater than Bob, Alice is the answer. If Bob is, let's say, greater than Alice, now what will happen? If Bob is greater than Alice, then obviously Bob will always win except under one condition. If Alice, because Alice takes the first move, if n is less than is equal to Alice's number of stones, Alice can just take every stone and he'll win. So if n is less than is equal to Alice, Alice wins. Else, sometime Bob will get his chance and he will kick Alice's ass. So in that case, Bob would win. But the interesting case is Alice equals Bob. What will happen then? Okay. So in this particular case, this particular position is a losing position, right? It is a losing position. Why? Because there is no element over here. So that is why we call a losing position. And you'll hear this often if you are trying to solve problems of game theory, winning positions and losing positions. If you can make someone reach a losing position, if let's say there is this position and you can force someone to go to a losing position, then this is a winning position. So these concepts you'll hear again and again if you're going through problems of game theory. So this is a losing position, and because n is equal to 3, let's say Alice and Bob are 3, both are 3. Sorry, not n is not 3, n is, let's say, 12, but Alice and Bob are 3. Then if Alice is over here, Alice wins. He just take this stone and he wins. If Alice is over here, if n is, let's say, 2, Alice takes both the stones and Alice wins. If Alice is over here and n is equal to 3, Alice wins because n can just take these 3 stones and win. But if Alice is over here, if he takes one stone, Bob can take all these 3 stones and win. If Alice takes 2 stones, Bob can take the next 2 stones and win. If Alice takes 3 stones, again Bob can take this last stone and win. So what is Bob doing? If Alice take this, Bob will take all these 3 and force Alice to come to a losing position, right? So all these positions are winning positions. Why? Because any person, Alice or Bob, if is standing on these positions, can force the other person to come to the losing position. So these are winning positions. And this particular position is a losing position. Why? Because no matter who is standing over here, he can never force the other person to go to the losing position. He can only force the other person to go to a winning position, because if he removes one, he'll be over here. If he removes two, he'll be over here. If he removes three, the other person will be over here, and that is a winning position. So you'll see a pattern that it is something like this. So the losing position comes after every Alice plus 1 steps. It comes after every Alice plus 1 steps. So that's it. So if n, or yeah, if n is Alice plus 1, or for that matter Bob plus 1, because Alice and Bob are same right now, Alice would win. Sorry, Alice would lose, else Alice would win. So let's go to the code. We take Alice and Bob, the value of Alice and Bob. By the way, Alice in the program is A and Bob is in the program is B. Alice, when I say Alice and Bob, I mean number of stones Alice can take from the pile and number of stones Bob can take from the pile. If Alice is greater than Bob, Alice wins. Else if Bob is greater than Alice, then if Alice is greater than equal to n, so in this case Bob should win, but because Alice, the number of stones Alice can take is greater than the total number of stones, Alice just takes all the stones and wins. So that is Alice. That's why Alice wins, else Bob wins. Or else, if n modulo Alice plus 1, so if n is a is divisible by Alice plus 1, then that is a losing position. It is a losing position position and Bob would win, else Alice wins. So thank you so much for joining me on this solution discussion, and see you around. Take care. This is Utkarsh from Illinois, Chicago. If you want to join my if you want to connect with me, you can connect with me on LinkedIn. You will find the link of my LinkedIn on the description of this video, and see you around. Take care.